I am sure many of you have learned about geological time scales in your geography class or somewhere, or you have watched a nice video somewhere and so on and so forth. But in this context of past climate changes from the book we are using, the main book we are using here, I have to add a little bit more information since the book is a little too brief. So if this is a repetition for you, you can listen and enjoy, or you can skip the podcast and go to the next one. What are we showing here? There are many such schematics which nicely show how the Earth's history has evolved over time from the time it formed 4.6 billion years ago. So Earth forms 4.6 billion years ago, and you see there was no life, and it just looks like rocks and continents and oceans and so on. We call it the Archean, which is comes from the Greek word archis, which means the beginning. This is the beginning of Earth's history. It went on till about 2.5 billion with a B, 2.5 billion years ago. So you are coming forward in time. You're starting way back at 4.6 billion years ago. That's a lot of zeros. And then you're coming forward to 2.5 billion years ago, when we begin to see some evidences of life. They are not really fossils. Nothing gets stored that long, because Earth moves, the Earth's continents reform, ocean crust gets reformed, and so on and so forth. So the fossils tend to disappear, and at best you find things that are about 200 million years old in terms of fossils. But you get other chemical evidences, or things that are etched on rocks or printed into rocks or preserved in some other way. So somehow you are doing some detective work and inferring these things. So that period from 2.5 billion years ago to 542 billion years ago is called the Proterozoic, which means early life. And then you have the Paleozoic, which means old life. And then you have Mesozoic, which is the middle life. And then you have Cenozoic, which is, you can think of as new life. And here where we are in the Holocene for the last 10,000 years or so. So coming back here in Proterozoic, there were early forms of life. Many of them probably lived in the ocean, when we probably had already found ways to photosynthesize. If you know the details, or if you're old enough to follow up, then you know that the mitochondrion that every cell has burns the sugar to produce energy, and plastids, or the chloroplasts, take the sunlight and CO2, and they produce the sugars. And the algae that photosynthesize, or the leaves in the trees, have these plastids and to photosynthesize, and also mitochondrion. We also have mitochondrion, because that's how we produce energy in each cell as well. Okay, and you also know that you do some kind of a photosynthesis. What is it? Can you think of it? We take sunlight and we produce vitamin D. So we are photosynthesis just means use light energy to synthesize biological material, and we are producing vitamin D. So don't feel bad that plants are doing all the photosynthesis. Okay, so in the Proterozoic, maybe late in the Proterozoic, around 540 million years ago, there were some jellyfish-like things in a period called Ediacaran, which is from Australia, where some evidence was found. Jellyfish-like things, which are what? They are mostly like a dome. If you draw axis through the center, there is no left or right. It's a circle. But as the Cambrian arrived around 542 million years ago, there was an explosion of life, because oxygen had increased in the atmosphere and so on. Some 25 million new species are estimated to have appeared at that time. So that's called the Cambrian explosion. And in fact, this period after the Cambrian starts is called the post-Cambrian, and before that is called the pre-Cambrian. So you can see that bilateral symmetry arrived. So many insects, you see flies, bees, butterflies and hornets and wasps and so on. If you draw a line from the head to the tail, they are symmetric on both sides of that line with wings and patterns and whiskers and so on and so forth. So there's a nice gene called the homeobox gene, or the H-box gene, that evolved. Actually it's called the homeobox gene, that does this symmetric axial symmetry as opposed to radial symmetry. So just some details along the way. Ordovician, Silurian, Devonian, Mississippian, Pennsylvanian and so on in the Paleozoic. Plants evolved because sea level changes, maybe through some algae in the ocean that were photosynthesizing onto land, and some of them survived and started to do photosynthesis on land. And what did they have to do? They had to put down some roots to take up nutrients and water from the soil, and some of them started growing taller because they were competing for light, and they affected climate as well, because of course they changed the surface and the winds began to feel the vegetation. But more importantly, when they do photosynthesis, they take up CO2, they produce some oxygen, and if you draw down a lot of CO2 with lots of trees exploding around the world, you end up taking down so much CO2. Remember, CO2 is a greenhouse gas. If you reduce a lot of it, you are now like taking off the blanket and it's cold, then you are going to feel cold. Similarly, Earth got cold because the thermal radiation started to escape to space, and then you got a snowball Earth that we talked about before. Earth froze all the way down into lower latitudes. Okay, plus lots of material, organic material, carbohydrate and sugars that got formed from photosynthesis fell down and then got buried, and they were not respired, so nobody ate them and converted them back into CO2. So that hydrocarbon or carbohydrate and sugar got compressed and became coal, and then it became petrol and gas over time and so on. So a lot of the coal comes from that period around Pennsylvanian, and there is a Carboniferous and so on and so forth. And then comes the gigantic extinction because of those sorts of things. We don't always understand why mass extinctions happened, and mass extinctions have a definition. Some 90 or 95% of the species at that time, as we can estimate with our detective work, have to disappear in our evidence to say that was a mass extinction. So there is a PT boundary here between the Permian and the Triassic that caused a gigantic extinction. There are 5 mass extinctions along the way, and here is the other big one that you probably know. It's called the KT boundary, the KT extinction, which was a big extinction. That's around 65 million years ago, and you know exactly what happened at that time. You probably read about dinosaurs and saw the Jurassic Park movie and so on. So you had the Triassic, the Jurassic and Cretaceous from about 250 million years ago to about 65 million years ago, when this massive meteorite crashed and maybe created a lot of dust and fire and viruses and diseases and so on, and killed off all the dinosaurs. But life continues, so mammals became dominant and we began to evolve at the very last moment here. Okay, here is some nice dinosaur flying around. Is that the T-Rex? You know better than me, right? You can send me a message saying, Grandpa, that's a T-Rex or not, right? Because I'm not a dinosaur expert and I haven't read so much about the dinosaurs. I did see the movies, okay? So here come the Paleocene, Eocene and so on and so forth, and here we are in the Holocene. Pleistocene had many ice ages up and down, and that's when our ancestors like chimpanzees and gorillas and so on also evolved, you know, much before that. But we began to walk around maybe around 2 million years ago or more, and that is on 2 legs. We are different from chimpanzees and gorillas because they mostly walk on all 4s, but we mostly walk upright, except when you're a baby and you're crawling around, right? So as soon as you're able to walk around, you stand up. And we are called bipedal, and they are called quadrupedal. Horses, cows, dogs, pigs, chimpanzees, gorillas, they are all quadrupedal. They walk on all fours, right? So think of this billions and billions of years of evolution, and we appeared at the last moment. Here we are sitting and talking about what a big impact we are having on the planet by burning everything that was produced before and consuming oxygen and releasing CO2, which is a greenhouse gas, and we are causing global warming, right? Well, you are still young, so you didn't do much, but your future is going to be affected by what we have done. So you have to think about it. You are the future. The future is yours. So we'll come back and add more details from the British Geological Survey on the things that we can look at in a bit more detail. So you can skip if you're happy with this much detail. But good thing about YouTube is that everything is a little podcast, so you can watch the ones you want to watch and skip the ones you want to skip if you think you already know it, or you may listen again and say the grandpa sounds a little bit excited, let me see what he is saying, right? Ask questions of your teachers, parents, siblings, neighbors, and send me a message if you want. Okay, enjoy, kids. See you in the next podcast, continuing this discussion on climate changes through Earth's history.